So we've seen an example of a myth which attempts to explain natural phenomena. Let's take a look at a more scientific theory, Newton's law of gravity, or Newton's law of universal gravitation, to give it a more accurate name. It's important to understand just how revolutionary this idea was. It's often thought of as just this thing that tells us that things fall down to Earth when we let go of them. But it's actually a great deal more than that. What Newton's law of gravity allows us to do is explain the movement of apples and other objects falling down towards the centre of the Earth. But it also allows us to explain the motion of the moon around the Earth, the motion of the Earth around the Sun, the motion of all of the other planets around the Sun, the motion of other planetary moons around their host planet. It even explained, and Newton used it to explain the motion of a comet, which is much more complex. It has a very elliptical orbit which takes it from far away from the Sun to very close to the Sun. It's a very, very powerful theory which explains all of these phenomena with a simple mathematical expression. Let's look in a little bit more detail at how Newton's law of gravity actually works. Basically what it says is that if you have two weights, equal weights, separated by an equal distance, then there's a force between them. So here's one weight over here. Here's another weight, both equal in mass, and there is a force between them. Now, if we increase the mass of one of them, let's say that we double the mass of one of these two weights and keep the other one the same and keep the distance between them the same, then the force between these two weights is going to be double what it was before. If we reduce the distance between the two weights, going back to our original weight size, but halving the distance between them, then this increases the force by a factor of 4. So when we halve the distance between the two weights, that actually increases the force between them by a factor of 4 times. So it may not be immediately clear how this relates to the phenomena that we've said are explainable by Newton's theory of gravity. So let's take them one by one. First of all, the idea that we have weight and that we're pulled down towards the centre of the Earth. Well, it's the huge mass of the Earth which is pulling down on the comparatively much smaller mass of your body or whatever's being pulled downwards. So actually, when you're standing up, like I'm standing here, every part of the mass of the Earth within the core and all around it is pulling me towards that mass. And the net effect of that force is to pull me down towards the centre of the Earth. What's maybe a little bit more difficult to understand is how this single force can explain the roughly circular motions that we have, for example, of the moon or a satellite moving around the Earth. So the way to think about this and link it in with our everyday experiences of how things fall on Earth is to imagine someone throwing a ball or maybe a projectile being fired from a gun. What we see is that when that projectile is fired, it moves in a curved shape up into the air and is slowly pulled down towards the ground. There is a constant force of that projectile down towards the centre of the Earth. Now, we tend to think of downwards as always being the same because the Earth is so big, its curvature is so small that we don't really have an intuitive feel for the way that we're not actually being pulled downwards, but we're actually being pulled towards the centre of the Earth. So how does this change the movement of a projectile? Well, the fact that it's always being pulled towards a central point is what makes it move around and complete the circle. So the movement of the Earth around the Sun, the movement of the Moon around the Earth, the movement of satellites like the International Space Station around the Earth can all be described with exactly the same simple theory which just says that every mass in the universe is pulling on every other mass in the universe. As we've seen, Newton's theory of gravity explains a wide range of phenomena. At the time that it was invented, it didn't have anything that seriously contradicted it. It fitted in with all known facts. So it was a very solid scientific theory. It also had a very simple mathematical expression. Now, this isn't an absolute prerequisite for a scientific theory. They can be a little bit more abstract. But the advantage of having a simple mathematical expression is that you can come up with quantitative predictions. We know, for example, that if we double the mass of an object, then the force of gravity should be doubled. So we can actually come up with some real numbers to test our theory against new evidence.